Sumeet Kulkarni. I'm a master's student in science at IISc Pune, and I'm doing a project in astronomy at IUCA Pune. Come join me on a little journey as I show you what I work on. In the 17th century, in Italy, Galileo Galilei became the first man to point a telescope to the night sky. It was a turning point in the history of science. Man had acquired a new eye to observe the universe. Today, we are in the midst of a similar era. It's a new beginning in the world of astronomy. New advancements in technology have brought mankind to the threshold of turning a new eye to the sky, an eye to detect gravitational waves.
What are gravitational waves? Albert Einstein, through his general theory of relativity, published in 1915, established gravity to be not a force, but the effect of massive bodies causing bendings and distortions in the dynamic fabric of space-time. Accelerated motion of massive bodies in this fabric creates ripples which propagate through it. Precisely our gravitational waves.
The waves created by ordinary objects like you, me, the Earth, or even ordinary stars are extremely feeble. However, there are instances that the supermassive objects like black holes and neutron stars exist in pairs and spiral into each other towards a collision. These compact binary coalescences emit gravitational waves strong enough to be detectable by current technology. LIGO, Laser Interferometer Gravitational Wave Observatory. These are large detectors which can detect the gravitational waves, the ripples in space-time. Now, as soon as these waves are detected, it is our job to try and locate their source in the night sky. Observing the gravitational wave sources in visible and other electromagnetic frequencies will give us a lot more valuable information. But LIGO, which detects the waves, cannot tell us exactly where the source is in the sky. So we do not know where to point our telescopes. Let me show you how it works.
It's like the game of pinning a tail to the donkey. I am in a room, blindfolded, and there's a picture of a tailless donkey kept at a place unknown to me. The picture, and in particular the point where the tail goes, represents our source. The wall itself is the entire sky. Now, a whistle is blown from where the picture is hung. This sound represents the waves detected at LIGO. Till date, without any detectors, we were deaf to all signals passing through space. If I were a single-eared creature, I may hear the sound. I know how loud it is, I even know its frequency, but that doesn't tell me in which direction it's coming from. I don't know where the donkey is. I'm sad. But since I have 2 ears, by computing the difference in the waves coming into each of my ear, I can easily determine the general direction of the sound source. Similarly, a single gravitational wave detector cannot tell us where the source is in the sky. But by studying the same signal from multiple gravitational wave detectors, scientists can localize a patch in the night sky where the source may be present. This patch is like the huge area on the donkey's posterior. It is divided into a grid of cells. The cell where the tail goes is somewhere in this grid, and each cell is just large enough to take in the pin of the tail. For our telescope, the size of the pin is equivalent to the frame of the telescope. That is, the area of the sky it can cover in one image. Our job is to locate the source inside this patch. We continually probe the patch, one frame at a time, till we find the source, till we pin the tail. If I get it in the right donkey hole, I win. Yay! But there's a catch, which makes this game even more interesting. After a certain period of time, the picture of the donkey just disappears. I cannot hope to observe the source.
Because compact binary coalescent sources are believed to be transients, their signal, their image, will fade over time. Also, the patch in the night sky inevitably sets at some time owing to the Earth's rotation. Hence, it is vital to start the observation process immediately after the first gravitational wave signals are received. So now, we are working to program robotic telescopes to automate the process of taking in information from LIGO and observing the night sky without any loss of time. But here, we are faced with several questions. Which frames in the grid to observe first? How to schedule our observations if the patch is about to set? Do we always observe the cells having maximum probability first? We are trying to figure out the best algorithm to schedule our observations and hence increase our chances in finding the source.